The facility location game. We now turn to our second example, the facility location game, and let's observe how the standard primordial scheme for this problem fails to satisfy cross-monotonicity. Recall that LP formulations 15.3 of the facility location problem and the observations that one can assume without loss of generality that in a solution to this program, we have that beta ij is equal to the maxima chosen between either the value 0 or the values of alpha j minus dij. And in designing a primordial algorithms for the facility location game, we think of the quantity maxima of 0 and alpha j minus dij as the contribution of agent j toward the facility I, and say that a facility I is tight with respect to the dual solution alpha. If the total contribution I receives in alpha equals its opening cost, i.e. if the summations of the maximum summing for all j in A, where the maxima is taken among the choice between 0 and alpha j minus dij, such kind of summation is equals to fi. Then we call it tight. Now following the general paradigm of the primordial schema, let us consider the following algorithms for computing cost shares in the facility location game. Initialize that the cost shares alpha j to 0 and gradually increases them until one of these two events occurs. The facility I goes tight, in which case this facility is opened, and the cost shares for agents j with positive contributions to I are frozen, i.e. no longer increased, or for an agent j and a facility I that is already opened, alpha j is equal to dij, in which case the cost share of j is frozen. This process continues until all cost shares are frozen. To illustrate this algorithm, consider the facility location game in example 15.2. That is in figure 15.1. Call FL cost share is in this page. In this example, at time 2, facility 2 goes tight as each of B and C makes 1 unit of contribution toward this facility. Therefore, the cost shares of B and C are frozen at 2. The cost share of the agent A continues to increase to 4, at which point facility 1 also goes tight and the algorithm stops. In this example, the cost allocation 4 to 2 computed by the algorithm is budget balanced and satisfies the core property. In fact, it is known that in every instance, with a post-processing step that closes some of the open facilities, the cost of the primal solution can be brought down to at most 3 times the sum of cost shares, and therefore the cost shares are 1/3 budget balanced on every instance of the facility location game. However, unfortunately, the cross-monotonicity property fails, as can be seen in the example in the figure 15.1. In this example, if only agents A and B are present, they will both increase their cost share to 3, at which point both facilities go tight and the algorithm stops. Hence, agent A has a smaller cost share in the set AB than in ABC. Intuitively, the reason for the failure of cross-monotonicity in the above example is that without C, B helps A pay for the cost of facility 1. However, when C is present, she helps B pay for the cost of facility 2. This, in turn, hurts A as B stops helping A as soon as facility 2 is opened. This suggests that the following way to fix the problem: we modify the algorithm so that even after an agent is frozen, she continues to grow her ghost cost share. This ghost cost share is not counted towards the final cost share of the agent, but it can help other agents pay for the opening cost of facilities. For example, in the instance in figure 15.1, when all 3 agents are present, even though agents B and C stop increasing their cost share at time 2, their ghost share continues to grow until at time 3, facility 1 is opened with contributions from agents A and B. At this point, the cost share of agent A is also frozen and the algorithm terminates. Final cost shares will be 3, 2, and 2. The pseudocode of this algorithm is presented in the figure 15.4. Variables alpha prime in this pseudocode represent the ghost cost shares. With this modification, it is an easy exercise to show that the cost shares computed by the algorithms are cross-monotone. However, it is not clear that the budget balance property is preserved. In fact, it is natural to expect that having ghost cost shares that contribute toward opening facilities in the primal solution but do not count toward the final cost shares could hurt the budget balance. See, for example, exercise 15.3. For the facility location problem, the following theorem shows that this is not the case. Okay, first let's see what the algorithm FL cost share says. For the FL cost share, the input is the facility location game AC, this is the instance, defined by the facility opening cost Fi, and the distance is Dij. Okay, set T, which is subset or equals to A, of agents that receive the service. And what's the output? The output is the cost shares alpha j for every j in T. Okay, then it runs as follows. That is, for every j, initialize both alpha j and alpha j prime to 0. And at the beginning, we assume that f is empty set. And while all those t removing f is not equals to empty, then we do the following. We increase all alpha j's for all j, which is in a t remove f, and alpha j primes for all j in a t at the same rate, until the following two conditions that we have to check. First, for an unopened facility A, the summations of the maxima chosen between 0 and alpha j prime minus Dij, summing for all index j in T, is equals to Fi. So that in this case, we open facility I and add every agent j with a positive contribution toward I in F to F. Now for the other cases like that, for an open facility I, that is, and the I is opened and an agent j, alpha j is equals to Dij. Then in this case, we just add directly agent j to F because it does not need to contribute it to for the further opening of the additional new facilities. So that's it. Now let's see what the theory 15.21 says. Theorem 15.21 is that the cost allocation computed by the algorithms FL cost share in figure 15.4 is 1/3 budget balanced. Okay, proof is as follows. It is enough to show that for every instance of the facility location problem, it is possible to construct a solution whose cost is at most 3 times the sum of the cost shares computed by FL cost share. To do this, we perform the following post-processing step on the solution computed by FL cost share, and let Ti denote the time at which facility I is opened by FL cost share, and order all facilities that are opened by this algorithm in the order of increasing TIs. We proceed in this order, and for any facility I, check if there is any open facility I prime that comes before I in this order and is within distance to Ti of I. If such a facility exists, we close facility I, otherwise we keep it open. After processing all facilities in this order, let F prime denote the set of facilities that remain open and connected each agent in T to its closest facility in F prime. We now show that the summations of alpha j, summing for all j in T, is enough to pay for at least 1/3 of the cost of this solution. Let Si denote the cost. The set of agents within distance Ti of facility I. First observe that for any two facilities I and I prime in F prime, Si and Si prime are disjoint. So these facilities, the set corresponding to the agents opening for the two facilities, they are disjoint. They are different agents. And this is because if there is an agent J which is in, as I intersect Si prime, the distance between I and I prime is at most Ti plus Ti prime. Ti plus Ti, which is less than equals to 2 times the maxima chosen between Ti and Ti prime. So, and therefore, one of I and I prime must have been closed in the above post-processing step, because they are too close. To complete the proof, it is enough to show two statements. First, we show that for every facility I which is in F prime, the cost shares of agents in Si is enough to pay for at least a third of their distances to I, and hence to their closest facility in F prime, plus the opening cost of I. Second, we show that each agent J that is not in the unions of Si, where the union is for union all those index I in F prime, can pay for at least 1/3 of its distance to its closest facility in F prime. To prove the first statement, note that for every facility I in F prime, the ghost cost share of every agent contributing to I at the time of its opening is precisely Ti. Hence, the summations of Ti minus Dij, summing for all j in Si, is equal to Fi. Therefore, if we show that for every j in S, such that alpha j is greater than or equals to Ti divided by 3, we will get that our expected results from the theorem, that is, the summations of alpha j summing for all j in Si is greater than or equals to 1/3 times Fi plus the summations of Dij summing for all j in Si. Now assume for contradiction that there is an agent J with alpha j which is less than Ti minus, divided by 3. And consider the facility I1 with Ti1 equals to alpha j, i.e. the facility whose opening has costed the cost share of j to freeze. There must be a facility I2 in F prime that is within distance to 2 times Ti1 of I1. So if I1 is in F prime, we can let I2 equals to I1. Therefore, the distance between I and I2 is at most Dij plus Di1j plus 2 Ti1, which is less than or equals to Ti plus 3 alpha j, which is less than 2 Ti. This contradicts the assumption that I is in F prime, since I comes after I2 in the ordering and I2 is in F prime. To show the second statement, consider an agent J which is in T, removing all the set Si, where the unions of Si is for all those index in F prime, for those index I in F prime. So we unions all those kind of Si, and let I be the facility with Ti equals to alpha j. There must be a facility I prime in F prime that is within distance to Ti of I prime can be the same as I. Therefore, the distance from j to its closest facility in F prime is at most Dij plus 2 Ti, which is less than or equals to 3 times alpha j.